Hello, everybody. I'm Jon McLoone, and I'm speaking to you live from the Wolfram Research UK office. You can tell from the light out my window, it's getting a little later. It's my great pleasure to give you a first public preview of what's new in Mathematica 13, something that I guess it's only been 7 months since we last had a feature release of Mathematica, but there's quite a lot to talk about. I can't cover it all in this session, so I'm just going to talk about some of the highlights and things that I wanted to draw your attention to. You can ask questions through the chat system, and I will try and take them live, but I will certainly try and take them at the end when I finish presenting, which will take perhaps an hour to get through all of the things that I have to talk about. So I'm going to share a notebook here, and you are now seeing Mathematica 13 on screen, and let's get started. So the first question always is, what's the kind of the big feature or the point of a particular release? And we always have a challenge of creating new functionality to take our vision of computation into more domains, but also to improving the infrastructure and functionality for our considerable existing user base. And as always, we're trying to balance all of those things. So there isn't really a single key killer feature here. There's improvements across the board. In total, there's about 150 new functions, depending on how you measure that. And we've got improvements across particularly data science, but also increasingly verticalized areas like engineering and biosciences and chemistry. But there's also quite a bit this time in what I've labeled here as maths, but really I think of it as the infrastructure that powers everything else that we do. So sort of core parts of the system have been improved, and then of course there's improvements to the Wolfram language itself and general connectivity. So it's hopefully something for everyone, no matter what your background is. There should be something in this release to interest you and improve your working life. So I listed here data science as a start point. So I'm going to come in from that angle somewhat arbitrarily. And if we're talking about data in general, then of course the start point is we've got to get data into the Wolfram language to be able to compute with this and get the insights that we want. While it's not the most glamorous part of the system, where we constantly improve things like import-export, we're now at 246 different formats supported, mostly bidirectionally, some of them just for import or just for export. In this release, we're adding some scientific formats, a new raster format for import only, so we can pick up legacy flash video can be imported. But even for things that we already had imports for, we're constantly trying to improve performance and the details. So there's now additional subparts, the metadata you can access in things like WebP and HEIF formats. And perhaps the one that will excite most people is PDF import, which of course we've had for a long time, but now we have the support for importing vector content, not just the text and rasterized images. We can get proper vector art in from PDF. So here I'm doing a remote fetch of something from the archive repository, and this is a particular page from PDF. But you can see as I rescale it here that we've got while the images were bitmaps, the text here is coming in as completely kind of vector image overall. I put it in data because very often data includes timestamps, but really this is for the kind of space engineering and astronomy set. We have extended our support for time to cover high accuracy time systems. And what I mean by that is if I take this kind of standard time reference and put it into one of these high accuracy time systems, TAI, you'll see that this midnight on the 1st of August in the other system is midnight and 37 seconds on the 1st of August. Because if you are in the high accuracy world, you care about leap seconds and the kind of wobble of the Earth as it spins and the wobble of the Earth around the sun. And no 2 days are exactly the same length because of these things. So these seconds are added in and adjusted to try and keep different time systems in sync with reality. And we've now got support for that with historical data so that you can do very reliable time conversions. And then perhaps at the other end of data, we've got kind of increasingly we're plumbing in all kinds of real world data sets. There are some new entities in the system, but perhaps the most fun one here is that we now have real-time FAA flight data. So I can do this query here and say what flights went between JFK and LAX today. And we've got a list of flights here that have been queried, but more than that, we can actually query the flights themselves. I can get the first of those flights and ask it for the map of where that flight went. And assuming its flight has been completed, and I assume that that flight was early this morning, New York time. Yep, there we go. We can see that flight has been completed. This is the route that it took just north of the Champaign office. And you can see that it gradually got faster through the journey before it slowed down in its descent. So that adds in with the thousands of other data sets that we have, like chemicals and weather data and financial data and enzymes and proteins and all of these things that are built into the system. As you can tell, it's a kind of a long-term strategy just to keep adding in more and more of these useful data sets in a ready-to-compute form. Now, as we go through our kind of data set workflow, the kind of next obvious thing you do with data is visualize it. We have a great system for visualization already in Wolfram Language, but there's still always more to do. This time, rather than specialized visualizations, we're adding in some more generalization on the existing visualizations. So we have now quite broad support for panel layouts. We had this, I think, for one function in 12.3, but in Mathematica, there's a whole collection of these functions that you can give this chart layout to that says, ensure that they are on the same X and Y ranges. So even though there's plenty of empty space at the top of this plot, it's given it the same range, they line up perfectly, and then it's factored out the axes so that I can read the axes once across the entire panel, and that works in 2 dimensions as well. And as I say, across quite a few different visualization types as now. We also have a generalization for several graphics of multi-axis support. So this is the ability to plot multiple streams simultaneously, but have each one on its own axis. So the blue line here is on a range of 0 to 25, and the other two on their own ranges from 0 to 10 and 0 to 100. And actually, this makes redundant a resource function I wrote for the function repository that was dual axis plot. But you'll see here that this multi-axis arrangement supports any number of axes. So I've got 3 in this case. The default, of course, is 1, but if I want to, I can have 6, 7 axes. At some point, it becomes not very helpful. It becomes harder to read, but there's kind of an arbitrary number of these things is possible. And in a way, it's an exercise in automation, because with a single option, we can do all of the rescaling of the points, the rescaling of the axes, the arrangements of the axes, and the coloring, without having to kind of do all of that low-level code by hand. And another generalization on axes is, for a while, we've had these scaling functions. So you can scale over log regions or inverse regions or reverse regions. We now have generalized date. So instead of just having the one function date list plot, now all of the visualization functions can be given axes that are done in dates. So here I've just put some random numbers down, but by telling it that it's a date axis, it's interpreted those as of periods of time since January the 1st. And if these were labeled in absolute time, it could be over any period of time. And so it'll automatically decide to break it at days and months and years, depending on what's appropriate for the scale. And again, because it's a scaling function, this works over many visualizations, not just, in this case, contour plot. And another extension on these scaling functions is this neat little thing of being able to plot over infinite ranges. And so we have a kind of extreme log plot kind of scale that gets increasingly compressed up to a point that it chooses as infinity on the plot in plus and or minus directions. So in a way, this is a sort of typical example of, I think, when we're doing our job right, is there are actually no new functions here at all. You know, list contour plot has already existed, scaling functions existed, but there's quite a lot of new functionality here without having to invent new functions. And this is a much better way of doing things than the kind of traditional way back in the 1990s, where we had a log plot and a list log plot articulating all of those things by factoring them out of scaling functions, it becomes more powerful and easier to use because there's less to remember. Now, some of these visualizations and operations on data depend on the context. Spatial data is something that we started building out, I think, around the beginning of version 12. And there's still a little bit more landing in that spatial statistics area. The main thing here is a rich model for spatial estimation, often known as kriging. So let me give you an example here. I've got some data here that are ozone measurements across North America, but for some historical reason, they've got a lot of gaps in of where they haven't been measured. So the thing we might want to do is to build some kind of estimator, effectively a kind of interpolation function for guessing what's going on in those missing spaces. And spatial estimate is one of these super functions that brings together control over several different aspects, because we can independently give models for, is there a trend, is there a local effect, is there a random noise effect, and we can model each of those separately, depending on our knowledge of the situation. That perhaps ozone needs to have a localization effect, because if you're in a city with a very high ozone level, maybe that's a sign that the neighboring points will be, up to a 5 or 10 mile range might be highly influenced, but not over a 200-mile range. So once we got this, we can resample it and we can fill in our gaps. So this is just making some random positions and using this predictor function that we just created to fill in our prediction for at a higher resolution and filling in the spaces. Now that's very much on the computational side, but if we're talking about spatial data, one of the big domains of spatial data is really on a geo scale. And so there's been some improvements in Geographics to visualize that as well. This one's kind of subtle, but actually is another example of this trying to extend functionality, but without a proliferation of functions. We've had geo backgrounds for our maps for a while, but they've been a kind of take it or leave it kind of option. So you had the option to say, okay, I want to show a map and it's just going to show coastlines, not country borders. Or we want to have it with road maps on and so on. What we're starting to do is to break those down into components so that I can give now multiple backgrounds and say, okay, I want coastlines, but I also want some labels, or I want to mix country borders and labels, or I want to mix satellite maps and country borders. And all of these different permutations can now be specified out of these more component level backgrounds, rather than simply having, here's a pre-rastered background with the labels in. And you get side effects that are beneficial as well. It's putting labels on separately means that we can ensure they don't overlap even under weird map projections, and they don't get distorted by map projections, because they're always going to be, however the world is squished by the projection you've used, the wording will always be clean and vertical and untransformed. There is one minor new visualization type here, which is geograph value plot. We've had geograph plots in 12.3, which allows you to show flows, but now we can show flows with magnitudes. So these might be kind of migration patterns or something, or kind of shipping of products, links, but we can show that there's a lot more traveling down this route than there is over this route, for example. And we've also made it a little bit easier to throw on things like arrows and lines and circles onto a geographic as an afterthought, but making them accurately geoprojectional. Actually, let's do this example after all. So here's a very simple georegion value plot of some countries, but I'm throwing on a little afterthought which says, maybe you don't know where London is. I'll put a 2,000-mile disk around London. And the fact that that is not a circle in this particular map projection is now automatically handled. So these kind of epilogue type operations now consider the map projection rather than sticking a round circle on top, as they might have done before. Okay, let's start going through other domains of data now. Something that's been a big area for us for a while is image processing, and more recently video processing. And there's more work happening in that area. Let's start with the images. We have a complete framework of functionality for image alignment. So new techniques for figuring out what points within two similar images appear to correspond to each other. New framework for projecting images according to specific distortions, And actually what those add up to at the top of the stack is this sort of automated function for image stitching. And perhaps I should have started that earlier, that is doing the kind of thing that your mobile phone does when it does panorama photos, where I can take a collection of pictures and through the process of finding corresponding key points, figuring out how to project the images, a little bit of blending and fading, we can create this spherical projection of the joined up images as if I've spun the camera around. But of course, we're not really in the world of trying to make panoramic pictures for your photo album. What we're trying to do is to do sort of more computational work with image processing. So in our world, it's a little bit more important to think about what does it mean to stitch. If I'm standing there swinging a camera around, a spherical projection is the right thing, but we've allowed all kinds of control over what's allowed to be done in terms of how we join these pictures together. And so this affine option here tells us that in this case, the camera has moved physically. Perhaps it's attached to an aeroplane that's traveling across this viewpoint. And so in order to get the right projection, we don't get a kind of sphere forming around us, we get a flat plane. But it has taken into account that the further distance is moving more slowly than the near distance. And so you can see there's different stretching going on here, but using strictly affine, not spherical projections. And there's a couple of other choices. Now, video was fairly recently added, and anyone who's been in our ecosystem for a while knows we're fairly obsessive about making sure things join up. So there's a bunch of work that's happened in version 13 to make sure that that things that work on images will work automatically on video as well. So now if I do something like image take to crop an image, I can just feed it a video. If I put that video into an image effect like charcoal, it will just work. I don't have to start writing code that says map this image operation over the frames of the video, but leave the sound system untouched. That just happens automatically. And so here is a video where it's done both cropping and the charcoal effect in a single line of code. We've also added a whole bunch of utilities for generating video more easily. So they sort of are things like being able to put picture in overlays, overlaying text or static images, putting grids of video by video and tours. Easiest thing to show you examples here. Here I've overlaid a spiky onto a grid of variously time staggered versions of the same video. And so here is a grid version of a sort of preview of the video. And this is what I mean by an image tour. It's the kind of pan and scan problem. I can, I didn't actually need to run this, but it's going to recompute it here. I'm finding all the faces in the image. I'm finding a shortest tour of those. And then I'm using this new video utility to make a tour video whose position is width is fixed at a certain size over time, but its position changes over the time. And the effect is this little video snippet that will visit every face in the picture in order in the shortest path. So when you want to kind of programmatically control how you use images, whether they zoom out or pan across or combinations of those, you can set fixed points in time and values throughout to programmatically set up that video. Now, probably the bigger thing on the video space is as we step now into the top end of the highest level of data science, the machine learning framework that has been a really big deal with Wolfram Language for a few years now. One of the big important join-ups that we've done here is to now make video classification something that's supported within the language. So in 12.3, you could use an image classifier on a video, but you were looking at individual frames. And in the video classification, we want to take into account the whole kind of temporal value of watch the video and say, what is going on in this little snippet of video? And if I get the system running on it, it will watch the video and now make some kind of prediction about the contents of the video based not just on what it sees in a frame, but the motion going on as well. And it's made its prediction of barbecuing. And of course, these neural network models are just pre-trained models in our network framework. So if I get this here and open the thing up, you see we have the full neural net specification. So you can retrain it yourself on your own video content. You can analyze its behavior. You can do net surgery on it, try and improve the model, or transfer learning and those kinds of things, just like you can with all of our other neural net examples in the Wolfram Net repository. Now, the next one is the beginning of a longer term story, but there's two already very useful versions of it, which are content detectors. So this is a kind of new, fully automated super function of machine learning to go with things like predict and classify that try to do essentially everything for you if you give it the training data. And they're all about sub-contents recognition. So in this toy example here, I'm taking a phrase, but I'm telling it the characters 8 through to 13 represent a fruit. So this word is a fruit, but it's a fruit in the context of this sentence. And I can give it a set of those things, and let's do this one live. I will run the trainer because it's a tiny amount of data. We get a content detector function that we can now apply, in this case, the text that it hasn't seen, and it's able to pick out things it sees within the text. So for a long time, we've had these entity detectors where I can say, here's a piece of text, tell me all of the chemical elements that are mentioned in the text, or all of the cities that are mentioned. You can now build your own content detectors like that can teach it, tell me about medical conditions that are mentioned in this text, and have it figure out which phrases are the important ones to extract out from all of the noise. The other one that we have, which is a little bit expensive to run, so I won't do this live, but it's exactly the same concept, but in the image space, is you give an image and you give a region that you declare what that contents of that region is. In this case, there's two regions simultaneously in the same picture. There were two apples within this image, and this one has one strawberry within it. And then you can give unseen images, and you can detect which subparts of the image are the entities that you're looking for. So while you could do this kind of behavior if you rolled up your sleeves and knew how to use the neural network framework, we now have this as essentially a one-stop function. Just give it the data correctly marked up and let it think, and everything else is done for you. Now, one of the things I often say about our neural network framework is we're kind of trying to play both ends of the game. That we want to have super functions like the one I've just shown that are so automated that if you can understand the concept, you can use them without any domain knowledge. And at the other end of the spectrum, we are trying to give expert level tools for those who really want to get under the hood and tinker with the machinery of the machine learning and want to be able to control everything. So content detectors are really automated. The video classifier is kind of either. I think the explainability is in the middle of that space as well, that you can ignore this issue, but it's something I know from giving talks. A lot of people ask about explainability, and we've got two new, the classifier and predictor measurements and the net measurements have always been very good at giving very concrete information that is very quantified of things like what's the accuracy rate of a model. What these two new SHAP and ICE plots do is to give you a very qualitative feel for why. So here's the example to kind of make this make sense. I've done a classic demo example. I've got some data sets on wine quality, and I've used this fully automated predictor function to say, take that data, and we want to predict the wine quality column out of, I think there's about 10 measurements. And then we're going to use the test data that we held back to do predictor measurements on it. And then I'm going to ask for one particular measurement, which is this SHAP plot that is brand new in version 13. And here's the result that we get. And it gives us just a general oversight about which features matter in predictions. So if we look at the alcohol level at the top, we can see that how strong the alcohol is got the largest impact on the possible quality. It makes plus or minus about half a point to the wine quality. This is a quality score from, I think, 1 to 9 or 1 to 10. So it makes the biggest difference. And then the coloring is feature value. So what this is telling me is that when the alcohol level, for whatever reason, is saying this is a bad wine, actually there are lots of other ways to know it's a bad wine. That's a low feature value. Whereas when something's had a very positive impact from its alcohol quality, actually that's the strongest indicator that this could be a good wine. So you can see that some of these things have very low impact. Some of them, it's the opposite way around, which way the feature is valuable and which it isn't. Some, the feature is always of mixed value. So the residual sugar doesn't seem to be terribly important because it's never the only feature that tells us what's going on, neither is it a very impactful one. So if we wanted to drop a feature, maybe that's the one to consider getting rid of. The other one, the ice plot, tells us how does it impact. So if we look at fixed acidity, what we can see is that generally, as fixed acidity goes up, the quality of the wine goes down. So on the whole, you can see all of these lines are generally sloping downwards. And we can see that really it has no effect if the fixed acidity is below somewhere around 6. And it has no effect once you get beyond 9. It's not going to tell you anything new. We can see that with volatile acidity, there's a kind of bimodal distribution. There's a whole bunch of wines where it really doesn't make any difference. And there's a bunch of wines where, as the volatile acidity goes up, the quality goes down. And so we can do this across now at a glance across all of these dimensions to see what is good or bad. In some of them, it's not high or low. It's actually having a mid value for total sulfur dioxide. Too high is bad, too low is bad. The midpoint, the sweet spot for best sulfur dioxide seems to be around the 120 mark. More at the expert level of things, we've got improvements to dimension reduction, where you're trying to find a smaller set of numbers that accurately retain as much of the information about the data as possible. That's now about twice as fast. And there's a bridge between the two worlds in that these fully automated functions like classify and predict have been somewhat black boxes up to now. But if you are going to step up into the more expert world, you can now reach into those and grab some of the internals. You can do a fully automated predictor function, but then say, okay, I want to take the way that was encoded and take the encoder over to a different world, like a neural network built using the same encoder that was built for me automatically. So they're no longer two separate worlds. We're trying to bridge the gap so you can migrate or take knowledge from the fully automated and apply it in a more specified way. And automatic differentiation for custom layers. If you are going to invent completely new kinds of neural networks, you want them to be able to optimize quickly. And this AD, the automatic differentiation, allows totally custom layers that nobody's ever thought of using before to now train reasonably quickly. And obviously that's important to make them practical, but very much for the expert user, that one. Okay, enough of data. Let's talk about some other domains now. And I'm going to kind of zoom down to infrastructure and talk about some maths things, some of which are very mathsy, some of which are very broadly applicable. The first one I've picked on is kind of very small as a function, but quite big as a breadth of implementation for its applicability, which is centered interval. And centered interval is a new kind of arithmetic within the Wolfram language. So we obviously had arithmetic like numbers before. For a while, we've had arithmetic with numbers that have uncertainty. So around 3,1 says this is an experimental error. The number is 3, but it's plus or minus 1. And they propagate in an error propagation way. So the expected value of the error isn't the worst case of the two. It's actually basically the square root of 2. What we have with centered interval is something that's like a round, but more like interval, in that it always computes the worst case scenario. So in this trivial case, 3 plus or minus 1, if we have 2 of those, we end up with the worst case is 6 plus or minus 2. So that's obviously very easy to do in your head. But what we've done is we've applied that concept across a really large number of functions. So if, for example, I do sine on a centered interval starting with 3 plus or minus 1, the answer is now much less obvious. It's 0.07 plus or minus 0.83. And in fact, if I turn this up, you'll see that it becomes much more obvious again that centered interval 3 plus or minus 10, well, at some point, sine wave repeats itself. So it's just going to be 0 plus or minus 1. That's the full output range of sine. So what this gives us is a way of doing worst case scenario arithmetic. So if you have provable systems, you are in a world of super reliable systems, you need to ensure that numbers will never exceed some bound or some function is entirely predictable what its output range could be given certain input ranges, or the sensitivity of systems to inputs. Those things now become very amenable by this arithmetic that will propagate through all of the functions, or many of the functions within a complex equation or set of equations and tell you what's the propagation of that worst case interval. I'm going to skip through these quickly. We've got more in the way of linear algebra, so various kind of operations on matrices that if you recognize, you will care about, and if not, they are simply infrastructure to allow more functions that we make at a higher level to do things behind the scenes. The one that isn't a new function is least squares, which we've had for a long time, but now we have sparse data support. So when you have matrices that are mostly zeros, then we can do least squares on those very fast now without having to compute all of these zeros that have little effects on the outcome. So graph theory is a situation where that kind comes up quite a lot. You know, if you imagine a social network, there might be millions of people in a social network, but the average person is connected to no more than 50 or 100 other people. And so most of the connections within that network are zeros. So highly sparse systems are much, much faster to compute with. We have some new special functions, Coulomb and Fox functions. So if you're in the more theoretical maths and physics space, then we have these kind of very generalized special functions. But it actually interestingly marks a kind of a milestone for us, because the definitive reference on special functions is Abramovich and Stegun, and that's quite a venerable book now that describes the full world of special functions and some knowledge about how they behave. We now have computable support for all of the functions listed in Abramovich and Stegun. So we're almost done basically in covering special functions. We've already got the system that covers more special functions than any other system in the world, but we now reached the point of having decent support for basically the lot. And for us, support is arbitrary precision arithmetic anywhere in the complex plane that makes sense. Things like symbolic values and being able to differentiate and integrate where it makes sense. And while there may be still some more room to improve those, it's not just enough to make something that will evaluate for real numbers. Coverage has to be quite broad for our vision of special functions. Now, if you don't care about those things in their own right, then one of the things that they do is they help to power all of these sort of higher level solvers that are very popular within the system. So, for example, symbolic integration can benefit from this kind of growth in special functions because there are certain things that cannot be represented in closed form without special functions. We already had the best symbolic integration in the world, but as well as improvements in the infrastructure powering it, we've also got new support for algebraic functions and better contour integration. So here's an example that I picked out that we couldn't do in even though it doesn't look very complicated, we couldn't do in any previous version of Mathematica. And in fact, if you look at the world of kind of computer algebra systems whose sole purpose is to do things like algebra and calculus, essentially none of them can solve this particular integral today, apart from one very deep research system, which is way behind Mathematica in general coverage, but happens to be able to do this one. RSolve, again, another powerful solving function for recurrence relations. There's now linear systems with polynomial coefficients can all be covered by RSolve now, so a very broad class that is essentially finished. The n-minimize and family of optimization functions have more methods, and this has really just been a general story of the last few releases, that our optimization routines have existed since the very beginning. FindRoot, I think, was the first in version 1.0 of Mathematica, and you know they've been reasonable optimization and increasing coverage over the years, but in the last few years we've started targeting industrial scale. So when you have systems with many thousands of constraints that might be a mixture of linear and nonlinear or integer constraints, then the largest problem size that's feasible has been a constraint. And that's why there are kind of $20,000 systems to do just industrial optimization. So we are pushing back on the point at which you're leaving the scale of Wolfram Language to encroach on the territory of those highly specialized large-scale systems. I can't claim that we're better than them yet, but that's where we're going, and we've made really big inroads in recent versions to be able to go from working with many hundreds of unknowns to tens of thousands of unknowns in feasible time. So there's a bit more going on in that. The story isn't finished. There's a little bit more in DSolve, solving symbolic PDEs, and more ODs have been added. And I think at this point we can claim now to be the world's best at symbolic differential equation solving across even above these sort of specialized computer algebra systems that only do algebra and don't care about machine learning and data science and image processing and video and all of these other things that we do. So I think that there's several of these things that have reached kind of new thresholds of world beating, and others where it's still out of reach, but we're getting there. Right, let's narrow down the domain a bit now, but still in, I think, a math space. Graph computation has obviously been around since the beginning, but there is still always more to add. It's a big field. And we also recently added the concept of native tree representation as a specialist form of graph. I think in version 11.2, the tree function arrived. So I think the biggest thing in graphs is some real improvements to isomorphism finding. Now, if you're not in the graph theory space, give me a moment to show you examples to make sense of these things. This has made possible now a really decent implementation of subgraph isomorphism finding. So what is that? I think of it as pattern matching for graphs. So let's imagine I've got a social network, and these are all the people who know each other, and I need to find certain types of people within that. And there's some experiment I want to do. Maybe I'm a psychologist, and I want to find groups where you've got 4 friends who know each other, apart from 2 who have not yet met. Can we find people a collection of 4 people that match that pattern within this data? And what that turns into is this statement here, to find a isomorphic graph from that graph that is subject to labeling identical to this graph. So we don't care what else it's connected to, and we don't care what the labels are, but it has to have the same shape as this graph. And there might be lots of them, so I'm going to ask for only 4 so they can fit on screen nicely. And it's found here 4 of these that person number 15, 2, 152, and 12 all know each other, except for 15 and 152 who don't know each other. So we've met our pattern. And so this is a very general bit of kind of infrastructure for searching graphs. Now, you might use that within a graph theory space, but I'll show an example in another domain where you don't really think of it as graphs, but like a lot of these infrastructures, it empowers other computations. And this is the real strength of our all-in-one philosophy. You know, if we lived in a toolbox or random libraries world, like some people believe in, then the fact that this would live in some kind of graph theory library or toolbox would mean that we couldn't rely on it from say, a chemistry toolbox, which I'll come to in a minute, which is the case I'm thinking of where this kind of thing comes in useful, because we couldn't assume that you have it. Or you end up with some big dependency tree that says, in order to use this toolbox, you have to have the right version of this other toolbox, and you have to disentangle those things. So all these kind of infrastructure, even if you use Mathematica only for the high level functions in quite a light way, you do care about this infrastructure because it's what powers everything else. Right, here's another abstract thing, vertex and edge coloring. This is how many or what ways can I color a graph so that the vertices that the neighbors aren't the same color, or the edges that join at a vertex aren't the same color. There's a classic theory with maps for planar graphs that you can map, color a map with only 4 colors. But if it's not planar, then it becomes much more complicated. So let me give an example to make sense of this. And my example is, supposing you want to set up some antennas, and they can't share the same frequency because they'll interfere with each other, and they have a certain range. How many frequencies do we need, and how do you allocate them? So I'm going to make my world here randomly. Here is my set of antennas, and you can see that these 2 are really close to each other, and they interfere very heavily. And they actually overlap with this one as well. This guy here doesn't overlap with anyone, so it can take whatever frequency it wants. Well, I can think about that as a graph theory problem, where overlap means connected. So let's do that. So here is the abstract graph that shows which transmitters overlap with which. And we have these new coloring functions that say, what is the number of colors that I need to color that graph? So we need 4 frequencies. How do I allocate them? According to, this is the frequency for vertex number 1, the frequency for vertex number 2. And if I color the thing back in, you'll see how that works. So you can see here, this is my first frequency that I use most. My second frequency I have to switch to in this case because it's overlapping with frequency 1. I don't have to worry about it overlapping with this one because that doesn't overlap with this. So in fact, we can get by with just 2 frequencies in this cluster over here. But over here, where there's lots going on, we needed all 4 frequencies to keep them all from interfering with each other. Another abstract thing, but again with very practical applications, is dominators, and we have the ability to find and measure dominator and dominator relationships. What is a dominator? Well, imagine I'm in a network world where I have communications that go down wires. A dominator is a failure point in my network. A dominator is something where I cannot reach a certain vertex like number 6 without going through number 2. So by finding the dominator tree, starting at number 1, we see that 1 is a dominator of everything. You can't get anywhere without starting. And 2 dominates everything else, but nothing else is dominated. So you can get to 5 without going through 4. So 4 does not dominate 5 because you can go round it. If this telephone exchange failed or whatever these connections are, you would still be able to get a message to number 5 because that nothing was dominated by 4. But if vertex 2 failed, then all of the things under vertex 2 would be cut off. So this is useful for finding bottlenecks and dependencies. Where is, if you've got a manufacturing process, where is the point where a queue forming will starve things downstream of supply? Where are the failure points? Things like that are all solved by dominator type graph problems. In a social network space, who are the influences over certain people that are dominators as well? Now, another one which is now getting more into the expert level is tree traversal control. So a lot of discrete problems break down into searching a space of solutions. So imagine you walk into some kind of building and you need to explore the building for some object that you're looking for. You have choices. You enter a room and there's multiple doors. Do you go all the way down the left-hand door of every room until you get to a dead end and then go back up to the top and down again? Do you go peek in each door first before you decide which room to go into next? These are kind of traversal orders for trees. And computer scientists talk about things like breadth first and depth first and so on. Well, we've given a really deep control. There are dozens of ways that you can control traversal order. So I've made a little random graph here. It's the same graph 12 times, but if I run this animation, you'll see that I'm exploring each graph in a completely different way. And if you have some understanding of where the solution is likely to lie or the cost of searching, then being able to control whether you go down the right-hand side or from the bottom up, level by level, that can allow you to optimize your search to give you a greater chance of finding the best solution sooner. That in the end, if you have to do an exhaustive search and visit every node, it's going to take the same length of time. But on the basis that you're searching until you find a solution early, you want to control the search path in order to improve your chances of minimizing the time to finding a solution. Okay, another mathematical, but again, very general domain is geometry. And you can think of geometry in its own right as calculations about shapes. But geometry is also the way that we express the real world to many of the solvers. So things like differential equation solving or integration or optimization can be constrained by 2 or 3 or 4D geometry. So you have to think about it also as an infrastructure for simply describing problems. But let's go through some of the things that are new in geometry. We've got some new region construction tools. So if you have a point cloud, and here is a very trivial point cloud that I've made simple enough you can see exactly what it is, surface of a sphere. This is fairly easy intuitively to see what the surface is that you would reconstruct. But computationally, there's different ways you can go about that. And we have these new concave hull mesh and gradient fitted mesh that are attempting to reconstruct surface from point clouds. So this comes up, for example, with LiDAR, that when you are scanning a world with LiDAR for a self-drive car, what you actually generate is a point cloud. Or if you're using your depth sensor on a mobile phone, you get a point cloud and you want to reconstruct what is the geometry of the thing in the real world that we're seeing based on a bunch of points that may or may not be actually connected to each other, because you don't really know what's going on between these 2 points. It's something of an assumption that they are probably attached if they're near to each other. Also in the augmented reality space, we have some very fast region fitting. So I've got some random points here, well, not totally random, but some points I've chosen, and I want to fit very quickly a circle to those, and here's what we've got. And there's a fairly small number of primitives, but in a kind of AR world, one of the things you want to do, for example, is to identify a plane. You want to augment some reality by putting some overlay on top of the table that you're pointing your mobile phone at. You need to be able to fit that surface very quickly, ignoring the errors in some points that might under or over measure distance, and likewise measuring best fit circles and so on. It's about doing it fast as well as much as it is about using about getting the value. And actually behind the scenes here, I talk about infrastructure empowering things. This kind of stuff is all improved by those industrial strength optimization functions that I talked about earlier. In the end, this is just an optimization problem, but by packaging up in a geometry space, we can make it pre-tuned to be very robust and very fast for that kind of problem. Similarly, again, as something of an optimization problem is region comparison and alignment. If you have two geometries, are they the same? And actually, there's several versions of the same. They could be exactly the same. They're right on top of each other, so they're exactly the same size, shape, and orientation. They could be congruent, which means that they're the same shape, but they might be a different size and a different rotation, and they might be similar, which allows more squishing transformation. So this simple example here, all my talks are full of toy examples here, is can we fit this peg through this hole? Well, the straight answer with the congruence testing is yes, but we can also do the transformation and say, what do we need to do to make it fit? And this is the rotation and shift required to make that, to move that shape so that it aligns perfectly with that shape. There's also a new bunch of ways of constructing geometries from primitives. So we can now support splines, which were of course invented for CAD type design. They were invented to make it possible to make smooth shapes like cars on a computer. So this allows us to interchange with CAD type data much better rather than having to approximate it as straight lines. Constructive solid geometry is a kind of Boolean way of building things up out of intersections and complements and unions of primitive shapes, again used a lot in kind of manufacturing type geometry. And then we've got some base primitives like torus just to fill out our space of the base elements. Now, I said that one of the things about geometry is not just geometry for its own sake, it's describing the real world. So that seems like a good segue into engineering. In the recent, so for some time we've built out a very good partial differential equation solver. In recent versions, we started layering on top of that high-level descriptors to say, I want to describe an acoustic problem with an acoustic reflection, and have that convert that automatically into the partial differential equations that you need to solve, so you don't have to get down and dirty in the details of PDEs. Kind of filling out that space now is we're adding primitives for solid mechanics descriptions. And again, the best thing I can do is show you an example here. This is just setting up some variables, and a parameter, which is, we're going to say the material is the element silver, pulling from our entity collection of materials. And then here comes the differential equation. NDSolve value, not a new function, but now it accepts this solid mechanics PD component to say, we've got a solid object, and there's a load on according to a boundary. So everywhere where x is greater than 1/10, we're going to put 100 newtons of negative force. So we're going to put some weight on the tip of the spoon pushing downwards, and we're going to fix the other end of the spoon so it can't move. And here is our spoon, which is a geometry from our from the mesh geometry that we've just been talking about. So this could have just been imported from a CAD package or scanned with a laser scanner, or maybe there's some equation description behind it, but it's just a little model of a spoon. And that's all we need now to be able to specify the deformations, the bending that will happen to this spoon. So here's the X, Y, and Z deformations across the space of the thing. We can compute with that. But perhaps the simplest thing we want to do is to see that. And we didn't have a good visualization for that. So added to the new visualizations, there's a collection of vector displacement plots that allow us to take a vector field, or in this case, a displacement field, and transform a shape according to it into a before and after. So here is our spoon before, and here is a somewhat exaggerated version of the spoon afterwards. And you can see that the tip where it's fixed has stayed fixed, and that the spoon has bent downwards. And if we did an extra computation, we could maybe color that with the stresses on the spoon, which I would guess are going to be most where it's bending somewhere here, what the maximum stress point is. But the ability to handle these kind of real world solid objects now in a high level way is really quite elegant and powerful. In the engineering space, we also have some new control theory, which of course is very important with our integration in with system modeling. And we now support for tracking problems, which is when you're trying to do a control problem, but you're taking into account the path that you get to the current position, not just where you're at. So if you want really smooth control systems like cruise control on a car that isn't constantly speeding up and slowing down, tracking problems are a way to do that much better. And in the signal processing space, we now have support for bilateral Z transforms, not just the one-directional Z transforms that we had before. Now, as we get deeper into the kind of more verticalized domains, everything kind of, perhaps not the, before I got into engineering, everything up to then was basically things that would apply to potentially to any user, whether you see it or whether it's behind the scenes. As we get into these narrow domains, there are things that if you're not a chemist, you won't care about, but if you are, we are out to try and build out a lot of these scientific domains in their own right, building on top of this infrastructure that we spent 30 years building. So one of the things that we have in chemistry now is substructure testing. And what this is molecules are just graphs of connected atoms. This is actually sitting on top of this graph isomorphism, subgraph isomorphism finding that I showed earlier, except that we can forget all about that graph theory basis for it. The idea is I can set up a pattern in terms of molecules. So this is saying a carbon and a nitrogen atom with a triple bond between them. So that's a cyanide component. And having set up that as a pattern matching exercise, I can look at a chemical that I've either constructed or fetched out of the 150,000 chemicals in our database. I fetched ethanol and said, is there a cyanide component, or is it free of cyanide? Is ethanol free of cyanide is what I'm asking here. And the answer is true, which is a good thing, obviously. And then here's the obvious counter question, which is a chemical like potassium cyanide free of a cyanide pattern? No, it's not. So this ability to take much more complicated pattern chemicals than these and say, in this complicated organic chain, is there ever an ethanol group or a benzene group within that? We can test for those kinds of things fast and in a very elegant way now. We can also take that concept of a pattern and use it in terms of visualization. And that's exactly what we've done with kind of enhancements to molecule plot, which is an existing function for a few versions. It makes a nice pretty picture in 2D or 3D of a molecule. But now we have custom styling on, I can style a particular bond, any bond that is a hydrogen-nitrogen bond, I'm going to color blue, and anything that matches our pattern, we're going to color red. And it allows us now to make these kind of much more pleasing, marked up 2 and 3D molecule things without having to carefully place a stadium shape on certain coordinates to make it happen. I can just have that marked up automatically. And also an example of kind of graph searching, we have this new find isomers, where I can take the molecule that I had earlier, which I've now taken off screen. Let's get that back. 3D. So here's the molecule that I used a moment ago that had the cyanide blob in it. There are different ways of arranging the same atoms with that are still chemically valid, and I can search through all of those and then make a molecule plot of each. So it'll take a few seconds to figure out all of the different permutations and eliminate the ones that can't meet the conditions of bonding, but hopefully after a few seconds, here's all of the isomers and a molecule plot of each of those. So I made those a bit small, but if I make it bigger, you'll see it has all of the same atoms in, but in a different arrangement. And the final thing in the chemistry space is a really first step at the moment that we have a symbolic representation of chemical reactions. All it does at the moment is the kind of school level chemical balancing. So if you're in education, it's useful, but it's actually a first step towards being able to do computations on chemicals. So here it is, in this case, it is balance the chemical reaction. Say, to make this work, we need 2 of these, what is this, aluminium phosphates and 3 of the calcium nitrates in order to make this chemical reaction balance. Okay, another domain. We're running out of time. Let's press on. Biosciences. We added fairly recently representations of DNA, RNA, and peptides. We've extended now to support circular versions of those. We can also support cross bonding within that, hybrid sequences and sequence collections of either disjoint fragments of DNA that are considered as a whole, or mixtures of DNA and RNA. And we have a new let's not do the example. We have a new visualization for those, and it's very contextually dependent. So you can see here that this is a small RNA sequence. We can color it in the same way that we can highlight molecules. But if we do a much larger one, you see it knows automatically to stop putting C's and G's and T's on it, and instead turn those into tooltips because they won't be visible when you have very small components. So typical kind of automation to try and make professional looking elegant graphs visualizations fairly easily. Right. Of course, all of this sits on the Wolfram language. So there's some improvements to the core language as well for you to express yourself. The compiler is a big long-term story for us. The aim is to try and take any Wolfram language code and compile that into machine code so they can run at kind of C or machine code level type performance. So you're going to hear this every year or every 6 months as we ship new versions that the compiler improves. So more things are compilable than before, they compile a bit faster than before. The stepwise things are we now have support for sparse data as a data type within the compiler. So as I said before, sparse problems, treat them as sparse problems can be done much, much faster than dense. And since the compiler is really all about speed, or mostly about speed, then compiler support for sparse is a significant deal for high performance. There's new data structures. These are collections of data structures that are not as general as list and association in the Wolfram language. But if you know that all you're ever going to do is to add to the back of a list and take from the front, then using a first in, last out data structure can operate much, much faster than one that has to worry about what if you're taking data from the middle. So there's a new data structure there and a couple of new operations that have been asked for by users on existing data structures. There's about 30 of those now, I think. If anyone uses Cloud Expression, which is our in the Wolfram Cloud database-like structure, you will see nothing different, but it has been completely re-implemented with a much more scalable backend. So instead of having to worry about what happens when you have more than a few thousand items in it, that will now scale into hundreds of thousands or millions of items without collapsing under the kind of load of data. And on the more convenience level, when you're doing parallel operations, you're distributing a chunk of computation like this search for a prime number over multiple separate kernels or remote machines. We now have this estimator on how much work is still to be done, how many kernels are operating, how many evaluations have been done, and an estimated completion time. Because parallel problems on the whole, it's a little bit easier than the general problem of predicting how long those will take, because you've already broken them up into roughly equal sized chunks, is the whole concept. And so when that finishes, you will get the result back. Oh, you won't, because I put a semicolon on the end, so we don't see it. Now, slightly different than the parallel computing, we have this fairly new remote batch submit. And the idea of that is to drop some large but non-urgent computation onto a cloud infrastructure that can scale as big as you want, and then you come back and pick it up later. So things like a machine learning training job that you might take 12 hours on, you don't want to have running on your laptop. You can drop it in the cloud and query it 12 hours later, say, are you finished? If you are, give me the result back. We now support Azure for that to go along with Amazon and Charity Engine backends. So obviously Azure is a pretty big cloud provider, but it's the same remote batch submit function that you had before. You set up the credentials, and then you just say, drop this computation on Azure, and it will provision the machine. It will set up a Wolfram engine on that machine. It will bill back the cost of the Wolfram engine to your cloud credits account, and do the computation and handle all the communication. So it's a one-liner to do all of that workflow. And if you're in the blockchain world, we are gradually adding support for all of the major blockchains. So as well as the big ones like Ethereum and Bitcoin that we've had since the beginning, we've added all of the framework now supports Cardano blockchain as well. Now, in the interface world, how you actually face the system yourself, we've got a little mix of different things that have been added. The first of those is now, for the first time, we've got proper, decent tools for you to be able to build beautiful documentation like the built-in documentation that we have. So that is partly set up for building documentation to go with a Padlet being a kind of collection of code and documentation and palettes and resources that we are now exposing the documentation for how to build Padlets to make it easier for you to set up, easy to install complex packages for other users, and there will be a repository to make it easier to share those in the not too distant future. So making it easy to make really nice documentation is part of that. On a much smaller scale, there's a side effect of that, which is a real kind of lightweight convenience. If you're in the help system now, you now have this little button in the top corner that gives you a quick access to one small slice of that documentation, which is create a new custom guide page. And the idea is that it builds you a template here where you fill it in with my favorite functions, and some description of it, and maybe my favorite function is plot, and maybe I have another function which is integrate, and maybe I'm going to explain to myself what those are because I always forget. And the idea is that under deploy, I can now make a built version of that documentation. Actually, let's just do it. I'm going to deploy that into my help system, and we can close that now. Don't need the source code anymore. And you can see now that I have I closed it there by accident. Did I say my favorite? I forgot what I called it. My favorites, there we go. So, actually, I was playing with this earlier. This is an earlier version of, this is my practice version of this. I've opened the wrong one, but this is what it looks like as a guide page, and these things automatically connect into the functions that they relate to. So you can make these kind of quick reference guides for yourself, and they will be searchable and discoverable within the help system, and should be appear underneath the menu here with to be able to quick reference. Somewhere here as well, we have, I think it was when I was in the new page, there is a palette. I'll give you a quick glimpse of that. This is the general tools, of which guide page is only one, building the individual function pages and tech notes, give you all the templates you need, and oops, sorry, I can't show you that right now. I have to set up a Padlet first, but they give you all the templates for doing all of the documentation in a similar kind of way. You just fill in the gaps and click build. Going in the opposite direction, you now have the choice to do without documentation. So when you download Mathematica or other Wolfram Engine instantiations, you get a choice whether you want local documentation or not, and it will automatically open help in a web browser using the web version of our documentation if you don't install it. But it means if you want to quick install, or you're pushing to machines that don't have much disk space, the vast majority of the install size, about 10 gigabytes of it, is documentation. So you can now leave that out and download much faster and have a less impact on your storage without actually losing any of the documentation, since you browse for it on demand. The question function for making quizzes in a kind of more educational context have been improved. There's sort of new question types and scoring types, but there is also one of these sort of template type setups where now you can very quickly author these things by saying, okay, I want to insert a question and I want it to be, well, let's just do a simple multiple choice question, and it gives you a template to fill in and you can preview it. and you can attach which are the right answers, generate a notebook that you can send to users, and you have a choice within that, or whether you have the marking done on the server or locally, depending on and the appearance of that notebook. You can do all of this by hand from the code level, but these sort of quick template things allow it to be much easier for you to make a kind of end of class quiz and then put it in the cloud and point all your students to it, and then they can take the quiz, and you can set something up if you know the questions you want to ask in a couple of minutes. Presenter tools, like I'm using now, our slideshow environment has been made much more robust, and it's things like interactive content within them are much faster. There's new plugins if you like IDEs. Personally, I use IntelliJ, but we have plugins for Sublime and VS Code editors now. So if they're your preferred IDE of choice, you can add plugins to have them mark up Wolfram Language correctly. And there's also, if you are cloud deploying, we have started adding some tools to make it easier to build web pages without having to resort down to HTML and CSS. So responsive layouts allow you to say something like, this dashboard in the cloud is going to be 3 columns, unless you're viewing it on a mobile device, in which case it'll be 1 column. Or the box on the left will occupy 50% of the screen, and the other 2 will occupy 25% each until they hit 300 pixels, in which case they will stop getting smaller, that kind of thing. But at Wolfram Language level, automating the contents into HTML. So trying to bridge the gap between very Wolfram Language-y notebooks and the very low-level HTML world. You can have things that kind of allow you to be in the HTML world without having to go low-level. So a little behind time. I hope to have finished in an hour, but I hope you can see there's a lot to talk about, and I've had to skim very fast over some of it. Those are the main things I wanted to highlight. The big question everyone always asks is, when is it coming? The desktop versions of it should, all the major versions should roll out gradually over the next week, with the first coming on Monday. There will be Stephen will be doing one of his long blog posts, which will no doubt cover features that I've skipped past. That should come out Monday as well. If you're a cloud user, the Wolfram Cloud is running version 13 already, and the online documentation is already on 13. So you can go to reference.wolfram.com and scroll to the bottom of the page and click new features, and you'll get a list of the functions that have changed, and browse those in great depth right now. So we are imminently about to have this fully launched. Across the summary really is, as you see, we've touched pretty much all of the major domains. There is work going on across many fields in the system, some quite minor incremental changes, some really quite big ones, some that are really automated and ready to use, others that are infrastructure that are there to set up future super functions and high-level functions, but are already available for you to use if you want to get more involved in the details. And a lot of things that we've got in here are only really possible because of that infrastructure building that we've done over the last 30 years. So this is a constant theme of the more we do, the more it makes possible. And that's our kind of long-term vision. If I had to sum up in half a dozen, I think these are my favorites. The solid mechanics, I think, is a pretty amazing functionality that used to be an entire purpose of a professional system before, is now just half a dozen extra functions in the Wolfram language. Content detectors, I personally am already using within projects that I'm doing with our technical services team, because I have a little team here where we do projects for customers who don't want to write their own Wolfram language code, and so I've been waiting for this function for some time. I think video machine learning is pretty cool, but I think the infrastructure as well is very important, that we are hitting these sort of key milestones where we are definitively the best in the world at all kinds of these things that, if you're a specialist, you really care about, but actually you should care anyway, because they all make everything else we do possible, and not just possible in the simple cases, but that they'll work in the complex cases. And I think spatial estimation is pretty cool. And I have to say quiz generation, because I've been involved in some of the design work and early prototypes on that. So I hope you find, as we roll more quiz stuff out over coming versions, those of you in education will make good use of it. So thank you very much for your patience. And having said that I would pay attention to questions as I went, I was totally preoccupied by what I was saying. So now would be a great time to ask questions. And I'm going to look back here and see what has come in so far. Can you create multiple axes with special axes like curved axes introduced in 12.3? No, the answer is no to that at the moment. This auto placement is going to assume vertical y-axes. I forget whether it supports axis scaling. I guess we could risk an experiment right now and find out, but it certainly does not support the very generalized placing axes that curve in any shape. Let's just see if we can do an experiment now. Where was it? It was on visualization. So we want to take the scaling function. Let's take the state one and apply it to the multi-axis plot and see if anything interesting happens. And yes, it does. Okay, so scaling functions can be combined with multi-axis plotting, but I'm pretty certain that curved axes cannot. Oops, I have lost the chat window. Can you use tick length within plot list plot such functions? Yes, so there are tick controls for style controls, and in the end you can roll up your sleeves and place ticks individually if you want. I mean, you wouldn't do it by hand as such, but you can write you've always been able to write these sort of programmatic ways to construct the ticks and the tick labels and the tick label styles and the tick sizes and the tick styles programmatically. Will there be also improvements regarding polar plot or list polar plot? I do not know whether these things that I've got here apply to polar plot or not. Again, I'd have to do an experiment. We'll try that in a minute. Compiler data objects and similar, very slow for large data. Is there a fix coming? Well, performance on data is a priority. I don't know what the data object is something that is on the list for compiler support. It may also be that there's one of the things that we're doing as the compiler matures is we are also applying the compiler technology to bits of functionality that are already in the system that are written in Wolfram Language. I mean, ultimately, the aim is that we should be able to point it at any Wolfram Language code. But one of the priorities is to find low-hanging fruits that feel where improvements would be beneficial, and using those as motivating things to say, what would we need to improve the compiler to make things like date difference faster. So I don't know what the status is on that, but it is certainly on the list to make that a reality. Is the Packlet repository coming with version 13? Not with the version 13 release. So some of the things in version 13 are done in preparation for the Packlet repository. The ability to make documentation being the one I highlighted. There's some new tools for management of contexts that seem a little specific to bother talking about in this, that are designed so that you can we don't have to worry about a kind of land grab for the namespace for context. So you'll now be able to import a package that's in context A, but declare it to be in context B, so that it can coexist with another package in context A. And that's again in preparation for this Packlet repository. I don't have a date for that. All I saw was the request to give all internal people access to the beta version of the Packlet repository a couple of days ago. So I'm waiting for my beta access so that I can play with it myself. So I haven't actually used it to tell you whether it is super finished and only a case of having to go through testing in a days or weeks away, or whether it's a bit further out. How to measure content detector accuracies. They do not yet have a direct analog with predictor measurements, because you've got a it's not so easy to have a notion of truth, because you can have a picture that says this has an apple in it and the apple is here, and your predictor has a go at finding the apple, finds an apple, but it's a few pixels bigger or smaller, what you would consider basically a correct answer. So they don't plug straight into those things that just say, the answer is this, the predictor said that, therefore it's right or wrong. So at the moment, validation on these content predictors is a task for you to do. There isn't any automation on that at all. What is the state of better integration of polyhedrons with a computational geometry framework? I'm afraid I don't know the answer on that. We will have to get you, if we have your email, make sure that you put that into the chat, and we'll get somebody to get an answer on that. Other questions? Oh, and I should mention that as well as Stephen's blog, Stephen will be doing his own live stream on Monday, apparently. Stephen will no doubt not try and fit that into a 60-minute space as I have, so you can expect much, much more detail and coverage of many of the things that I've skipped out. I don't know if Justin wants to tell me if there is an intended run time for that, or whether it's anywhere between 1 and 3 hours. Do we have a plan? Or you can certainly expect a much more thorough version, and in some ways more definitive version than I've given you, but in other ways simply a different perspective. I would allow plenty of time if you intend to watch the whole thing. Very good. Oh, so I missed, I think I've missed one here, which was, could you show more how to drill it into automatic functionality and tweak it? If I could remember what the syntax was, the basic idea is that we can use a classify in some automated way. Let's say that 1 classifies A and 2 classifies as B. Whoops. And we're making a classifier function. The question is, what's the syntax? I should be able to say something like CF. Can I say properties on this? No. Maybe it is when I give it a value. No, I'm forgetting what the option is. There is a way basically of saying things like, what is the, I forgot what the word is. The encoding function, I'm just looking at the documentation here to see if that reminds me. But as you can imagine, with a big super function like classify, there's quite a lot of documentation. I have not personally used this function yet, which is partly why I cannot remember how to reach into it. Can I say information on this? Is that the root to it? I'm feeling it's something like no, that's not helping me. Okay, the answer is no, I can't drill into that live for you. So it's the one can't know everything. So Seth, I'll try and dig out. I have your email already somewhere, so I will try and dig out a reference for you and point you to it. Any improvements specific for reinforcement learning? I'm afraid not. That's still something that you'll have to wait a little bit longer before we have a good solution to. And obviously one specific corner of that is the adversarial networks, which we've had some functionality on for a couple of versions, but there is nothing new in either direction. Okay, we seem to be running out of questions. Oh, I'm sorry, I missed a whole bunch further up. My goodness. Right, okay. Do student accounts of Mathematica get these improvements? Yes, so all versions of Mathematica get all the functionality. So if you are about to buy a student version, buy an upgrade to your existing one or have Premier Service on it, then all of this functionality will be available to you. We've never made cut down versions for students. I'm afraid I don't understand the question, how is this regulated? Perhaps you could rephrase that question. What's your favorite thing in 12.3? In 12.3, I think probably mean in this 13. I think it's it's probably the content classifiers. I think that's pretty cool. That whole process is a one-step operation now. It is relatively expensive, so GPU recommended or plenty of trading time, particularly when it comes to images. I mean expensive computation. I don't mean expensive money. Okay, there's a question about a notebook error, which I don't know anything about. We'll have to. I haven't even seen that error, so I couldn't comment. Code checking looks really great. So that's something that came in 12.3 actually, but is generally being improved as this functionality for being able to look at your code and find probable errors in it. That was recently added in, for example, into the later template for function repository items. So when you submit an item to the Wolfram Functions repository, it automatically checks your code on submission. That was very recently added, I think, and is within is a menu item within Mathematica. Yes, I don't know what the story is for why we don't have Voronoi Mesh 3D, because I don't understand that it's a particularly complicated thing, but we still only support Voronoi in 2 dimensions at the moment. You can do, you can of course make 3D meshes, and I suspect you could probably fairly easily prune those and simplify them into a Voronoi 3D, but it's not something I've got around to thinking about as a resource function. I will lobby for that one myself as a requested feature. Will there be a tutorial video made for the new video and AI features? If not, please do. There isn't immediate plans for that. We do have a general program of trying to improve the monograph documentation. So that's where we have these several different kinds of documentation. We've always been very good at the reference documentation. What does this function do, and what are its arguments? There is the tutorials, which kind of deal quite nicely with here's your sort of first 20 calculations that you do in machine learning. The monographs are the much more in-depth version of documentation that we've got some very good ones on, for example, partial differential equations. So I know there is a project to build out some of that tutorial and monograph documentation in a bigger way. And I believe that we have just shipped or just about to ship a really, apparently I haven't looked, I'm here by hearsay that a very good book on machine learning in the Wolfram language, written by the lead on the team for that. Justin will probably be able to tell me if that is actually out yet and what it's called. But no, I'm not aware of any video plans in the near future. Okay. Have I scrolled up too far up the chat? Now that will explain why somebody asked what my favorite feature in 12.3 was. Okay, I apologize for that. It shows how the last time I really talked to Justin was quite a while ago. Right, so there aren't any more questions. So thank you very much for the questions now and a year ago. And we will wrap up there. Do come back on Monday to see Stephen's take on the new version. Thank you very much.